last week, we was wondering what a cathode ray tube is. And we snuck into a neon sign factory. But first, I look at Phonograph records. Why don't we do a thing about cheese?
Boy, things sure have changed since Thomas Edison first invented this in 1877. Where have they? Edison's first machine used tinfoil wrapped around a rotating cylinder. When he spoke into the horn, his voice wiggled the air, and a diaphragm, a lot like an eardrum, wiggled a needle that was in contact with the tinfoil. As the cylinder rotated, the needle left wiggling impressions of his voice behind. Then he made the needle track over the same wiggles, and the needle wiggled the diaphragm, and the diaphragm wiggled the air, and the music industry was never the same again. It's a pretty far cry from a modern record player, isn't it? Nope. This 1980s version of Edison's first record stores sound in exactly the same way. You can prove this to yourself if you want. It's just an ordinary safety pin and a cone of paper. But try it with a record you don't care about, because the pin's pretty hard on those tiny wiggles. The biggest difference between how Edison made his first recording and the system in your house is electromagnetism. When an electric current's passed through a coil of wire, magnetism results. And the effect works the other way too. When a magnet's passed through a coil of wire, an electric current results. This is what the world calls a speaker. It's got a coil of wire wrapped around a magnet down there, and that coil of wire is attached to a cone of paper. The whole thing's glued together in such a way that the paper cone can move in and out with the coil moving over the magnet. If I apply a little current to the coil, cone moves out. If I reverse the current, cone moves in. That's how a speaker changes wiggling electric currents into wiggles in the air that your ear can hear. The same speaker will also generate a wiggling electric current if I talk into it. A lot of microphones use that principle. Here's a phonograph cartridge I made myself. It also uses the electromagnetic effect. It's got a needle-like object, it's a nail in this one, glued to a magnet. And the magnet's attached to a piece of floppy material that lets the entire assembly move. The needle and magnet are inside a coil of wire. Now, if the needle's dragged through a wiggly groove on a phonograph record, it will generate a wiggling electric current that matches the wiggles on the record. Now, for those viewers who think the props on Acme School are just a little funky and that a piece of copper pipe and a nail have nothing to do with a real phono cartridge, this is a mono pickup. Stereo uses two pickup coils mounted at 90 degrees to each other. This phonograph cartridge will also work backwards. If I feed it a wiggling electric current, the needle will wiggle along with it. One use of the backwards phonograph cartridge is the backwards record player. This machine doesn't reproduce the wiggles in a record. It takes a disc of acetate and cuts the wiggly groove into it. There's several reasons why it doesn't look just like a record player. Since its needle is cutting the groove, it has no groove to follow, so the cutting head is moved along by an extra motor. Its needle is heated to make it cut into the record better, and so it can't slip under the pressure of cutting. It's held onto the turntable by suction. The electric wiggles that will cut the grooves are fed into the cutting head and wiggle the cutting needle in a pattern that's the same as the wiggling air that hit the microphone in the first place, except for a couple of things. The deep, low-frequency sounds tend to make long, big wiggles. In order to pack more sound on the record, the amplitude of the low-frequency sounds is reduced. That's why the record sounds so tinny when you play it with just a pin and cone of paper. The amplifier in a player restores that missing bass. The louder a sound is on the record, the wider the groove will be. This machine predicts the future. It's the tape machine that's feeding the record cutter. An extra head on the machine picks up the signal before it reaches the main head, and it sends an advance warning to the motor that spaces the grooves to increase the spacing just before a loud passage. When this machine is done doing its job on the blank record, you have a record that's the same as the one you take home from the store, but you don't play this one. This is the piece of acetate that was on the record cutting machine. It's being washed. Now it's being sprayed with silver. The fine silver coating allows the acetate to conduct electricity. Why? It's going to be nickel plated. Electroplating is a method used to deposit fine coatings of metal onto things. When it's all done, it can be pulled off as a negative metal copy of the original that was cut. It's called negative because instead of grooves, it has bumps. This one could be used to press records, but instead, it's plated to make a mother. The mother is used to make the negative stampers. Why so many steps? To protect the original master from too many operations. A lot of stampers can be made from one mother. The stampers are carefully centered using a microscope and have a hole placed exactly in the middle. Records start their life as little pieces of polyvinyl chloride plastic. These are melted into lumps of hot plastic that look like cookies. They're called biscuits. The hot biscuit has two labels pressed against it. Then the biscuit's squashed between two steam-heated stampers that are the two sides of the record. Immediately following the squash, cold water replaces the steam under and over the stampers to cool the record. Now the record's spun for the first time in its life, and a knife trims the edge. It's complete. Well, it's complete, but the process isn't. Now it's complete. Talk about being the first on your block. I got the latest album by the hottest rock group before it was pressed. Recording sure has gotten a lot better. Too bad music hasn't. Neon signs first lit up the North American landscape in the 1920s. The magical feel and look can be traced back to the granddaddy of the neon sign, the lightning bolt. Both are officially an electrical discharge through a gas. In a way, a neon sign is a lightning bolt, tamed by tubing. The comparative friendliness of the neon sign comes from the low pressure in the tubing and the characteristics of the gases themselves. So-called neon signs are not all neon. The basic neon tube is clear glass with neon gas, the characteristic orange glow. Other gases used are mercury vapor, and argon. The rainbow of other colors used in signs comes from phosphor coatings inside the tubing, a lot like the phosphors in a TV picture tube. This is neon gas in a blue phosphor tube, pink. A white phosphor with mercury argon gives white, similar to a fluorescent light. This is pure neon in a stained glass tube, ruby red. Some tubes are double coated, phosphor on the inside and a colored filter on the outside. This assortment includes a clear glass on the left, followed by an inside phosphor, then several double-coated tubes, and a ruby red on the right. We found all these neon signs behind this neon sign. It's hard to describe a neon sign operation without using the word magic. The tools are magic, tube bending is magic, and the signs themselves are magic. I'll try not to use the word again. In order to see the tubing and the gas flame, these guys usually work in the dark. Having a TV crew visit and install lights is not their favorite way to work, but they were awfully nice about it. Tubing is bent into shape using gas burners. Depending on the bend, a long, adjustable length ribbon burner or a needle-pointed crossfire is used. A rubber tube connects the sign to be to the person doing the bending. Blowing gently into the tube prevents it from crushing as it's bent and sagging due to gravity. Now the test. Can Eric bend a sign with our lights right in his eyes? Forming tubing into a sign requires skill, the right tools, and planning. You can get some insight into the planning process by forming a piece of string into your own signature. The artwork for the sign's been traced onto a heat-resistant mat. How much of a curve or bend can be done at one time is a matter of experience and the look and feel of the glass in the flame. Once the tube's finished, electrodes are attached to each end. The electrodes are coated with a substance that gives off electrons readily. The length of tubing in the finished sign determines the size of transformer that will be needed to run the sign. This little sign contains 6 feet of tube. Now the sign's passed over to the mad scientist. Several things are going to happen here. The glass is going to be relieved of air and relieved of stress it got during all that bending. The electrodes are going to be cured at high temperature, and impurities will be removed from the interior of the tubing. This will all happen at once. The sign's attached through a small tube and one electrode to a vacuum pump. Sheets of insulating mica are added wherever arcing might occur, and a strip of paper is laid on the sign. As the pump removes most of the air, connection's made to the bombarding transformer. It's capable of 800 times the current of a normal neon sign transformer. Bombarding's a good name for this step. Lightning would be another name for it. The bombarding transformer causes the remaining air in the tube to ionize, conduct. This heats the glass and the electrodes. Bombarding continues until the glass reaches about 450 degrees Fahrenheit. That's what the piece of paper's for. Paper scorches at 451 degrees Fahrenheit. The sign's still being sucked to a high vacuum. When it's ready, the pump's removed from the circuit, and neon is released into the sign. Neon comes from a flask under the table. The neon in that flask is at atmospheric pressure, and only a tiny whiff of it is needed. This flask has enough neon for about 700 signs like this one. After filling, the small glass umbilical is severed, and the sign's connected to an ordinary sign transformer. The transformer for this sign will provide about 5,000 volts to induce the neon to conduct electricity. The instant that happens, the transformer's output drops to around 600 volts to sustain the friendly glow. Wonder what this sign says. Ah, magic.
Here, steady. Steady, come here. Nice steady.
You're looking at two of these right now. They're cathode ray tubes. That's CRT for short. This is one of them. The other one's in your TV set. Like all good inventions that were discovered a long time ago, cathode ray tube really isn't the right name for it. The basic effect was discovered before the electron was known about. In actual fact, they're focused electron beam tubes, but I just made up that name and it's probably not going to catch on. The effect takes place inside a glass shell with a vacuum, and the vacuum is necessary so that the electrons won't keep crashing into air molecules. Here's what's inside: an electron gun. Now, in order to keep the universe balanced, electrons like to go from where there are too many of them to where there aren't enough. A power supply connected to the gun supplies electrons to a heated metal plate at the back. It's called the cathode. The same power supply steals electrons from another metal plate at the front. It's called the anode. Because of the heat and the charges provided by the power supply, the electrons zoom off towards the plate at the front. When they get there, there's a big surprise. There's a little hole in the plate. And they go shooting out into space in a stream. The stream of electrons continues on until it hits the front of the tube. And inside the glass is a coating that gives off light when it's struck by electrons. Now, so far, all we have is a novelty light bulb that runs on 20,000 volts and isn't very bright. There are two more properties of electron beams that make this useful. They can be attracted and repelled by electrical charges. So a small mesh is installed near the cathode. Varying the charge on that mesh, it's called a grid, changes the intensity of the electron beam. A charged ring is also placed in its path. And by adjusting the charge on it, the beam can be focused. The second property of electron beams is that they can be deflected by magnetism. That's what the coils of wire on this one are for. They're electromagnets. By varying the current in them, the spot can be moved anywhere on the faceplate. One set of coils moves the spot in the X direction. That's engineer talk for sideways. The other set takes care of the Y direction, up and down. Your TV set uses electromagnets a lot like these. Here's some audio tones applied to those electromagnets. Now, that's one way to put a picture on a cathode ray tube. It's to move the spot around in various shapes, just like this. It's called a vector display. Some computer terminals and arcade video games use the vector display technique. Vector displays are easy to resize. Television as we know it uses a raster display. Now, a raster display is a repetitive pattern that gets brightened and darkened at the correct time. The television raster is formed by moving the spot from left to right 15,734 times a second, and vertically 59.94 times a second. The rectangle that results is made of 525 thin lines. This rectangle is synchronized right now with the camera that's shooting me, and there's one more input on my CRT, the Z-axis, or Z-axis if you're American. It controls the brightness of the spot. I'll connect the camera's video signal to it. A picture in glorious black and green. See, the CRT in my oscilloscope only has a green fluorescent coating on it, so all I can reproduce is shades of green. The color CRT is a fancy version of this. The color tube relies on the fact that most colors, including white, can be faked with the correct combinations of red, green, and blue. Now, this isn't like mixing paint because we're mixing light. It adds together. When you mix paint, it's subtractive. The color CRT uses 3 beams, and on the faceplate are different compounds designed to give off red, green, and blue light when the beams strike them. Now, there are various layouts of this. This particular one uses 3 guns arranged in a triangle, and the phosphors are arranged in groups of 3 dots. And behind the faceplate's a thing called a shadow mask. It has a single hole for each trio of 3 dots. Because of sort of basic geometry, one gun can only hit the green dots, and ditto for the red and blue. The 3 beams are swept across this pattern of dots, and their intensities are varied to produce all the colors you see. This particular monitor has switches for the 3 guns. Here's the red gun only. Red, white, yellow, orange, purple, and gray have a little bit of red in them. Here's the green gun. Here's the blue gun only. No matter what arrangement of color phosphors your set uses, all the colors you see are made up of a mixture of red, green, and blue light. If you don't believe me, just flick a small drop of water sometime on a color CRT and look at it carefully, or you can use a magnifying glass. There is a push to replace CRTs with other sorts of display devices, but so far they're nowhere near the brightness and sharpness of the good old CRT. So I think if you've used one of those display devices, you'll agree that the CRT is likely to be around for a long time to come. And listen, if sometime in the future you see a TV set advertised with a focused electron beam tube, remember, you heard it here first. It's interesting to go back almost 100 years to shortly after the invention of the phonograph. Some of this might sound pretty familiar. Enthusiasts argued over the merits of one or another machine, the dimensions of the acoustic horns, and the superiority of various needle materials. And believe it or not, Edison and others carried out live versus recorded comparisons in which the audience couldn't tell the difference. My favorite quote, though, comes from Sir Arthur Sullivan of Gilbert and Sullivan fame after he saw his first phonograph. For myself, I can only say that I'm astonished and somewhat terrified at the results of this evening's experiments. Astonished at the wonderful power you've developed, and terrified at the thought that so much hideous and bad music may be put on record forever. In the next episode, we're going to look at light bulbs.